New Zealand engineers working on developing countries problem, particularly in this case Nepal problem, and doing all the experimental work in Pakistan. Other thing is we are using the state-of-art technology to resolve or to understand very complex problem, complex building problem, to suggest or provide some very cost-effective, easy implementable systems. So before I proceed, so that's about this presentation. What triggered this research or this experimental work? So you may be aware of Nepal earthquake or Gorkha earthquake 2015, which killed something like 15,000 people, 9,000 people, and some 800,000 buildings were damaged or destroyed. It also damaged or destroyed some 30,000 classrooms, which required reconstruction. So of course, reconstruction, any material could be used for these school buildings, concrete or steel or low strength masonry or bamboo or timber. So there are a lot of options. But the problem is a large part of this earthquake affected area, something like 22,000 square kilometers, is spread over more than 20,000 square kilometers. Large part of the area is very inaccessible. So everything has to be carried by human or donkey or animal. I'm not sure how this donkey development will be sustainable. But the only construction material in those areas is timber, stone, and mud. Hardwood is not available, softwood is very prone to insects. And we can't treat this in those areas because no facility. We all know stone and mud are very vulnerable to earthquakes. Time has shown this scenario. In Pakistan, 2005 earthquake, something like 80,000 people were killed. Out of these, some 18,000 were children, and 500,000 buildings were destroyed. Nepal earthquake, 9,000 people killed, some 800,000 buildings are damaged or destroyed. In Dam, Iran, 2003 earthquake, there are some 32nd earthquake, 26,000 people were dead. So this is the scenario, but what is the solution? We have to construct a school building in Nepal, in remote areas, but the only material available is stone and mud. So of course we decided to use stone and mud. And the goal was to maximize the use of local material and with minimum import of modern material or cement and steel. And any material we use should be easy to carry. That was the criteria. And the building system we developed should be robust and resilient at the same time, easy to construct. So we decided not to do any radical change in the building construction system or the material. And we decided to use wires rather than bars and cement. Or some cement has to be used, but we decided to use wires. But here are more challenges. There are no research worldwide, globally, because we didn't invest in these type of building, and we always thought these masonry buildings are terrible, these are obsolete construction. So there is no research. So there is no design methodology. There are no standards, there are no codes. All our design formulation is based on continuum. These buildings always are in cracked state. When they are constructed, they were in cracked state. How we design these buildings, there is no methodology. Even we design what should be the compliance criteria. Should this be crack width or deflection or what else? Because when they are constructed, there is a 20-30 millimeter cracks already there. So these are the challenges. So we thought, okay, let's design something using any method, and then we will test it and shake them. So we developed some structural system using stone in mud mortar. From my observation in line 9 earthquakes I have worked on extensively, my observation is if we can maintain integrity of masonry building and avoid volume loss in any way we can, masonry buildings work perfectly well. They work very well, much better than many other building types. Though we have promoted them one of the worst building type, but that's not my observation. So we designed something using stone and mud, but we provided these bond beams to hold them together. These are very small beams because we have to minimize foreign material or the imported material to hold masonry together, the components together. But anyway, stone is rough material. they are irregular shape. So stone during shaking will come out anyway. And children sitting in the classroom, stone falling from the top of the classroom will be dead. So we decided to put mesh on both faces of the wall, as shown here, both faces of the wall, and tie them with these links. So the masonry is contained in the wire, in the mesh. So as long as it's contained in the mesh, we have prevented volume loss, maintaining integrity of the building, and building will perform extremely well. So time to do testing. So we did very extensive material testing, very extensive sub-assembly testing, and 6 set table testing. Probably, in my opinion, as far as I know, this could be one of the most extensive tests at a global scale at the time, at current time. So out of 6 set table tests, we did 130 scale, 3 models of each band type, because we used timber bond beam, we used gabion bond beam, and we used concrete bond beam. So for each bond type, we used 130 scale testing, and the models were testing to earthquake time history recorded in Nepal and to Northridge, one by one. And then we did 230 scale testing, but we could only test these models for 230 scale, for harmonic motion only. We did some numerical modeling also, but that we will discuss sometime later. This research was funded by the Asian Development Bank under a technical assistance grant to government of Nepal, and all the testing was done in Pakistan, because they have big set table, 8-ton and 60-ton capacity set tables. There are some testing models of sub-assembly, and you can see the difference of unreinforced without containment mesh and with containment. Maybe 1% drift, and you see the wall capacity is gone. Maybe it is at least maybe 8% or something drift. Still, it has enough capacity to maintaining the integrity. And as I mentioned in very beginning, if we can maintain integrity of masonry, building performs very well. We have not understood masonry building, though we have given it a very bad name. So now, time to construct models, set table models. So all the models are geometrically scaled to 230 and 130 scale. We use the same material as a prototype, and we try to reproduce the field condition, because of the masons constructed 2 good model. So this is a reinforced concrete bond beam, you can see. So this is one of the model. This is a 230 scale model, and you can feel the size of the model. It's inside room size is 3.6 meter by 4.5 meter, because it's a classroom. This is a gabion mesh, because a gabion, you can see the mesh. We put in stone, wrap it, close it, put more stones, because the goal is to maintain integrity of the building. This is a timber bond beam. Then, of course, once everything is done, then we put the mesh from outside and tie it to the walls. Time to do testing now. So this is a gabion bend, because the bend was very flexible, so all the interaction is going in the outer plane wall. Practically no damaging in plane wall. And you can now see the size of the model. It's a 3.6 meter wide and 4.5 meter long room, and it's a 230 scale. So we tested 6 models. None of them suffered any catastrophic failure or any instability. So we thought, let's do more tests. Because containment, the mesh is giving integrity and providing containment to the masonry. We thought, let's remove the containment and what happens. So from this wall, we removed 50% of the containment wires. You can see the wires here. So we removed 50%. And from other side of the wall, we removed 100%. So we did a lot of permutation and combinations. And then retested it again. These stones are also scaled to 1/3. This is a 1/3 scale model. So stones are also scaled to 1/3. So the stone height is something like 60 millimeter in rough order, very rough order. Let's see the test. building is perfectly well standing, still in occupiable shape. So what is the problem with unreinforced masonry building? We just need to do little bit and the building will show its beauty. And my long-term goal is to generalize the result and develop some simple methodology to design different shape of buildings. My other one is to extend these results to 2.5-story buildings because these are the most common type of buildings in Nepal, in hills and mountains. And then extend this to retrofitting of existing building using same methodology. So the summary now. The interventions made life safety requirement. Despite very intense and long duration shaking, it worked perfectly well without any unstable mode of failure, no catastrophic failure. Few stones fell off here and there, small stones, but no catastrophic failure or any instability. That's what it made building code, thorough building code requirement, though it may not have made building code in entirety. And I don't think it should meet, because these building codes are written for, not written for this type of buildings. They are written for concrete and steel buildings. So that's the first thing. We don't know what is the reserve capacity of the buildings or the models, because these all models survived very well. So they have enough reserve capacity. But the most important lesson for me or us should be how we disseminate this knowledge, how we take further knowledge to the people. And in my opinion, writing building standards or building code and guidelines are not a big dissemination of knowledge, or even presenting this paper is not dissemination in the real sense, because it has to go to the people. And people should be able to implement to make them safer. Until that happens, I think more than the world's 50% population is doomed. They are not safe. Because more than the world's 50% population live in this type of building. Low strength masonry building. In Nepal, there are more than 70% buildings are low strength masonry. In India, something like 80% buildings are masonry buildings. Same could be the case in Bangladesh. So this needs to be disseminated. As an acknowledgement and thank you. I'm not sure.
No, yeah, right.